I'll explain how to train large language models and get the best results with the fewest GPUs. This is relevant if you only have access to one GPU, or if you've access to multiple GPUs, but the model you want to train is just too big. Unlike LoRA fine-tuning, where you only update a small set of parameters, I'll focus on full fine-tuning, which gives the highest quality results. I'll first explain and then walk through some code examples of two classes of technique to reduce the number of GPUs you need. First, optimizer techniques, and second of all, gradient techniques. By the end of this video, you'll understand what training setup to use, given what GPUs you have and what model you'd like to train. All right, so before I start, there are two videos that you might want to watch in conjunction, maybe before, not necessarily, you don't necessarily have to, but the two videos are, first of all, my video on LoRA versus full fine-tuning. It explains the differences in quality that you get with each approach, and also goes into much more detail on LoRA, which is low-rank fine-tuning. It's a very, very popular technique, probably the most widely used technique. And I'm not going to talk too much about it today, although I will run a comparison just so you can see how these techniques compare with LoRA. The second video that's relevant is my video on multi-GPU fine-tuning. It might be called Fully Sharded Data Parallel, FSDP. It's a technique for splitting very large models onto many GPUs. That's also relevant if you are training a very large model, and those techniques can be used in conjunction with what I'm going to talk about today. So if you're interested in using fully sharded data parallel, and I explain why that might make sense later in the video, you also might want to check out the video on FSDP. So with that, today I'm going to focus on two things I haven't talked too much about, which are optimizing choices around gradient updates and around choosing the right optimizer. In the past, we just breeze over this and usually pick AdamW, and because we're doing LoRA, we're not using a lot of memory, so we don't have to worry too much about the memory for the gradients if you're doing a full fine-tune. So I'm going to recap here what gradients are, how they're updated when we train a language model, and what role the optimizer plays, and a few basics on the types of optimizer that are common. Then I'll talk about the memory, or the VRAM, that you need for doing basic optimization. That's stochastic gradient descent. We basically never use that, but it is the simplest way to optimize, so it's a useful ground study. I'll then explain the AdamW Optimizer and what memory requirements it has. It's explained in more detail in my FSDP video, but we will talk a lot about the memory requirements. We'll talk about how you can reduce those requirements by using 8 bits for the optimization parameters. Then I'll talk about a variant of the Adam Optimizer called Adafactor. It compresses some of the optimizer states in order to save memory and fit on fewer GPUs. Then I'll talk about Galore, a technique that came out within the last year. It's a way to reduce the memory you need for both your gradients and your optimizers. And there's now, just within the last few weeks, an adjustment to Galore that includes what's called Subspace descent. It's a way of doing Galore faster. There's a key aspect of Galore that involves a very slow calculation for doing singular value decomposition. We'll talk more about that later. But Galore with Subspace descent gets around that, and it also improves the convergence. So you get closer to just pure full fine-tuning like AdamW. Then I'll talk about one last technique, which is where you do layerwise updates of the model. This allows you to further reduce the memory, although it can reduce speed. It's kind of interesting for those of you who only have one GPU though, so I want to cover that just briefly at the end. And last of all, I'll compare the results on TensorBoard. I'll show you how all of these different models perform. Let me see if I can pull across. Yeah, I'll show you how all these models perform. I've run a lot of simulations, and we can compare the run times and also the quality of those models. So with that, let me quickly go through a recap of gradients and optimizers. And I'll do so with a toy model, the same as the toy model I used in the multi-GPU video. Let's consider a model that just has 3 weights here, weight 1, weight 2, and weight 3, 3 layers rather, and there's a weight in each layer. And what we're going to do when we inference, or when we run forward pass in the training, is we're going to take an input, use the weight to calculate the first activation, then calculate the next activation, then calculate the final activation. And when we get to the top, we'll compare the answer at the top, which will be our next token prediction. Now I'm oversimplifying here. We'll compare that with the actual token, and then we'll backpropagate the difference. That's backpropagating the loss in order to calculate the gradients that are going to be used for updating these weights. So we've 3 layers. we have these weights, we forward pass, we get a loss up here, and then we're going to back propagate, calculate the gradients, and update these weights here to values that the next time will lead us to be closer to the intended outputs. Now, in order to run this and to optimize the values of W here, one of the simplest ways we could do this is, in fact, let me just show you here what we're really doing. We've got a weight. So here's the loss as calculated at the very top of the network here. We calculate the loss, and our goal is to bring the weight down to some optimal position here. Now, of course, we don't know the shape of this curve a priori. What we do know is the gradient. So we can calculate the direction of steepest descent. So if you think about a bowl, we can calculate the direction that will bring us towards the bottom of the bowl. And what we want to do is take a step in that direction that will hopefully bring us towards the bottom. And that's essentially what the optimization process is. And the simplest way to do optimization is just what I said. You look at the direction at a direction of steepest descent, and you follow that for a small step. And so your new position for the weight, which will be somewhere down here, is going to be the old position minus some delta times the gradient. So that's how we make a very simple step update. And this kind of approach is what leads to stochastic gradient descent. You could vary kind of randomly the length of your steps, but basically we're taking a direction we're moving in the direction of steepest descent. And that requires us to store the weights. So we need to store what the old weight was. And we need to also store what the gradient is. So if we're working in 16 bits, that's 2 bytes because it's 8 bits per byte. We're going to need to store 2 bytes for the weights, and we're going to need to store 2 bytes here for the gradients. So very approximately, if you're working with a model, which I'm going to do today, I'm working with the Phi 3.5 model. We can look at it here. That's Phi 3. Here's Phi 3.5. Actually, this is a GGUF. So let's just put in Phi 3.5 mini. This model here, you won't see the parameter count. You can see that it's roughly about 7 gigabytes in size, and it turns out it's about 3.8 billion parameters. So very roughly, the amount of bytes we need is 4 times 3.8. So this is how you calculate the minimum memory you're going to need to train this model. It's going to be 15.2 if you're using stochastic gradient descent, which only requires you to store the weights and requires you to store the gradients. Now, it turns out that we do not use stochastic gradient descent because it tends to get stuck. It's too slow in updating when we get to plateaus, and it can also get stuck in troughs as well. So we use instead what's called AdamW. And AdamW is a weight decay version of Adam. So actually what we use is Adam, and then we additionally use weight decay. I've described in more detail exactly how Adam works, but basically it stores 2 terms. It stores a momentum term and an adaptive term. You can think of it like the history of the gradients and also the history of the variance of the gradients. And by using those, it's able to adapt when it gets to a plateau and kind of accelerate. And this gives a lot better convergence. So that's why we use Adam instead of using SGD. And the weight decay, that just means on every update, we actually reduce every single weight. We try and encourage the weights to be small so that we don't overfit. The weight decay doesn't really add much memory, but the fact that we store the history of gradients and the variance of the gradients, that does add a lot of memory. So actually when we use AdamW in 16 bits, we have to store the weights and the gradients, but we also have to store the adaptive term and the momentum term. And if we store those in 16 bits, yes, and often, by the way, they're stored in 32 bits, but if we store them in 16, that would be 2 bytes for momentum and 2 for the adaptive term. So we now have a total of 8. And so our memory requirement to train fully, to do a full fine tuning, has gone up to about 30 gigabytes instead of 15. And today I'm training on a GPU that has 48 gigabytes. So I'm starting to get towards the limit for what I'll be able to do fine tuning if I use the AdamW Optimizer. So one improvement, and it's quite a basic improvement, but rather than store these optimizer states in 16 bits, you can instead choose to store them in 8 bits. And this is what the AdamW 8-bit optimizer does. It will reduce from using a full 2 bytes for each of these parameters to using just 1 byte here. And that's pretty much as simple as it is. It will additionally store some scaling parameters, so it can expand from the 8 back up to 32 typically. So it will still do all the calculations in 32, but when we're storing the momentum and adaptive term on the GPU, we store it in 8 bits, and that saves us a lot of memory. So we're down now here to 5 times 3.8. So we've got 19 gigabytes plus some delta for storing scaling. And we may decide not to store every optimizer parameter in 8 bits. We may keep some of them in 32 bits. So it'll be more than 19, but significantly less than the 30 if we decide to store everything in 16 bits. So that's the first improvement, and I'll show you a run through with 8 bits. And actually, it doesn't affect the quality much at all in the example I'll show. It may be the case that if you're dealing with training a model with noisier data or right from scratch, it does pose issues. But from the example I'll show you, reducing this down to 8 bits does not reduce too much the quality. That brings us on to the next technique. So we're moving quite well here. I've gone through the AdamW Optimizer, which is the most popular one in machine learning for language models. I've gone through the 8-bit variant, which cuts down the optimizer size. Then I'm going to go through now Adafactor. So Adafactor is kind of a variant on the Adam approach. You can also put in weight decay, so you could do Adafactor W if you really wanted. And the idea around Adafactor is if you take this version of AdamW, the original one, instead of storing full matrices for the momentum and for the adaptive term, you just store averages of the columns and rows. So if you consider a momentum term or an adaptive term and it's a matrix like this, you don't store that. What you do instead is you store the top row here, the average, which is 2.5, the average of the second row, third row, fourth row, and the same for each of the columns. And if you do this, this is basically an approximate way to store the full matrix, because you can reconstruct an approximate matrix now by multiplying the row by the column average and multiplying that by a scaling factor. So just by storing the averages, you're able to rebuild a kind of rough original matrix that turns out to be good enough. And this is the key to Adafactor. Instead of having to store every single parameter in the matrices, you just store the rows and columns. And what you'll notice here is if this matrix gets a lot bigger, like 2000 by 2000, you're going to start saving a lot of parameters. And so Adafactor is, in principle, able to get down from having a full 2 bytes for momentum and adaptive term to having much less than a byte even that's going to be stored. And if you do the raw naive calculation, it would be 4 times 3.8 billion parameters in the Phi-3 model. Gives you about 15 gigabytes minimum of VRAM required, plus some delta, because you do have to store these averages for the matrices that you decide to compress. So this is Adafactor here. I'll talk a bit more about some additional differences to Adafactor. Adafactor means not just doing this, it also means that typically instead of using cosine decay, you will use 1 over square root of time decay. And additionally, Adafactor often will be set up so that it uses higher learning rates for large parameters and lower learning rates for smaller parameters. That's something I'll cover a bit later. It's actually a way that you can automatically set the learning rate just using these heuristics. So it can be kind of a cool choice. If you're not sure what learning rate to set, you could just run with Adafactor, deciding on the learning rate based on the size of every parameter. So this is Adafactor, and just notice that, yeah, in theory, it kind of gets you to similar memory as to going to 8 bits. Of course, in 8 bits, you're kind of making the representation of the optimizer states more rough via quantization, whereas in Adafactor, you're making it more rough by doing this averaging here. So that brings us on to the next class of techniques. I've talked about optimizer choices, and I've talked about these 3 optimizers, Adam, 8-bit, and Adafactor. Now I'm going to talk about ways that you can reduce the memory required to store the gradients. So we've kind of focused on reducing this, and now we're going to try focus on reducing the gradients. And the technique I'll cover is called Galore. And here's how Galore works. basically it says, well, let's say we have a gradient that's represented by this arrow. And for this example, I'm going to consider a 3D gradient. Well, Galore says, rather than represent this gradient or every gradient in 3D, let's just take the most important 2 dimensions and let's just use those 2 dimensions. So instead of storing this 3D gradient here, we'll just store a 2D version here. And then instead of doing optimization in all 3 dimensions, we'll just do optimization in the most important 2 dimensions. And what this means in practice is, whereas normally we might do optimization in 2048 dimensions with gradients, we will instead project it down to 512 or 100 or 256 or whatever. And we will do the optimization in that lower dimensional space. Now we'll pick the most important dimensions so that we get the majority of the benefit and don't lose too much information. But now we need to have much less memory to store those gradients. So this is what Galore does. It will calculate all of the full gradients, but once it calculates a new gradient, it projects it down to a lower dimension and will store it in that form. And the optimization happens in that reduced dimensional space. And because the optimization happens in the lower dimensional space, that's going to result in us reducing not just the gradients, but also reducing the number of optimizer states we have to save. Because remember, every parameter is going to have a gradient, and every gradient is going to have these 2 momentum parameters. But if we now do Galore, if we have, say, 1 billion weights, instead of having 1 billion gradients, we might only have 10 million gradients because we're in a lower dimension. And then because we've only 10 million gradients, we're only going to have 10 million momentum and adaptive parameters. So this is Galore. And the way, if you're curious, how we calculate which dimensions to focus on is using singular value decomposition. This means we take a matrix of gradients and we split it into a rotational matrix U and another rotational matrix V. And in the middle here, this is a diagonal matrix of singular values. If it was a square matrix, they would be eigenvalues. But the largest singular values represent the most important dimensions. So we just keep the singular values that are largest and we keep the corresponding vectors within the rotational matrices U and V. This calculation takes quite a bit of computation, and I think it's proportional to maybe the cube of one of the key dimensions. So as you start to run larger and larger models, if you're using Galore, every roughly 200 steps, if that's what you decide you want to recalculate a new projection matrix, then you're going to have this big delay because you have to do the singular value decomposition. And yeah, as I said, it's going to get worse as you train larger and larger models. So this is a problem, but it's a problem we're going to solve, or not we're going to, but somebody did recently in a paper I'll describe. For now though, what Galore achieves is it reduces the number of gradients down to a much smaller number because we're working in lower dimensions, and the same with the optimizer states. Just one caveat though, typically we'll only reduce the dimensionality of the linear layers. We won't reduce the dimensionality of the embedding layers. The embedding layers are, for example, what converts the original tokens into vectors and then vectors back to tokens at the other end of the model. And those are not linear layers, and we do not typically quantize them. We also do not typically project them to lower dimensions. So those will still take up quite a bit of memory. And so even though in principle here with Galore, we only have 2 full bytes that we need to store for the weights, giving us about 7.6 gigabytes minimum, the delta here will be somewhat large because we do still need to store the embeddings, for example, and in addition to storing the lower dimensional parameters, which save us a lot of memory, but will still take up some space. So this is the idea of Galore, and by reducing the dimensionality of gradients, it also reduces the space we need for the optimizers. And notice how we're still keeping the weights themselves in full precision, and we're also going to be updating every single one of the weights. This is unlike LoRA. In LoRA, we freeze the base weights and we create a small adapter that will then be expanded and applied. And that adapter is much fewer weights. And because there's only 1 gradient for each of those fewer weights, and there are 2 optimizer states for each fewer weight, that's why LoRA allows us to save a lot of memory. The problem with LoRA is that it doesn't allow us to update all of the weights, and so it tends not to reach the accuracy of full fine-tuning methods. So the last thing I want to cover on gradient methods is Galore with subspace descent before actually this bonus section here. Galore with subspace descent gets around the problem of that singular value decomposition. So I mentioned how you need to calculate which are the most important gradient directions. You do that with this expensive SVD calculation. And it's so expensive that you definitely do not want to do it every single step of your training. So you'll probably only update every maybe 200 steps. That's a typical value. And that's also going to lead to inaccuracy because it means that you're not updating exactly in the right direction. Every 200 steps, you'll get quite accurate, but then it's going to kind of decay as you move towards the next gap. I mean, you can always do fewer steps or update every fewer steps, but that's going to then cost you more SVD calculations. So Galore with subspace descent gets around that. And I should point out here that there are very nice GitHub repositories available. Here's the original Galore GitHub repo. I'll put a link to it below. And there include here some training scripts. And the same here in this online subspace descent. This is more or less a fork of the Galore repo, but it adds in this subspace descent technique that I'll talk about right now. So I mentioned if we do this SVD calculation to reduce the gradients, it's expensive. And the key realization of subspace descent is that it's cheaper just to do this once at the very start of training. And instead of recalculating what the low rank representation is, it's better to just find it via optimization. So it's actually cheaper to run a quick optimization problem than to do the SVD calculation. And that's particularly true if the matrices get large because you have, I think, this cubic relationship that the SVD calculation takes. So this is called subspace descent. It just means that once we calculate the most important gradient directions, we're now going to update what we think those are by using optimization. I know it's a bit meta, but there's basically there's optimization that's being used in order to pick the best dimensions in which we should run optimization. I know, a bit meta. So here's the trade-off. Basically, it's not a trade-off. It's basically all in favor of subspace descent. It's faster. It is slower initially because you have to do that SVD calculation, and you'll see that's why it bumps up for short training runs that are less than 200 steps. It's not going to give you much speed up. It has better convergence because you are optimizing the dimensions to optimize in every single step. And there is not really much VRAM difference. So there's not really a penalty in terms of memory for using this subspace descent technique. However, and I mentioned this already, it's still going to be slow for the first singular value calculation because it needs to calculate what the initial direction is going to be, or rather what the initial important directions you want to keep for the gradients are. And that brings us to a recap of all the techniques. I'll just talk briefly about this special one here, which is relevant for those of you who want to really pack as much as possible into one GPU. And it involves using a combination of Galore plus 8-bit plus AdamW plus subspace descent and Layerwise. So what does Layerwise mean? Well, typically when we forward pass, we've got the activations. And when we backward pass, we calculate the gradients. And then we would usually run an optimization step that will tell us how to update these values of W. But by the way, the reason that is good is because you calculate all the gradients, and now in parallel, you can set up all of the update calculations and make use of the GPU's multiple cores and do this very quickly. But you can also just work backwards layer by layer. So you can start up here with this activation, and you can work backwards and calculate this gradient. You can now make an update to this weight. You can now toss out what the old gradient and weights were and move down to doing the next step here. Do everything you need, toss everything out and move down to the next layer here. So by doing everything layer-wise and kind of tossing out intermediately, you're able to get the total memory that you need down because you no longer need to store all of these gradients and activations. So this is called working backwards layer-wise. The problem with doing this is it's less easy to parallelize. You don't necessarily need to do more calculations, but you do need to flush your memory more often, and it's just trickier to parallelize all the compute, so it will be slower. The other thing is it's difficult to use gradient accumulation. I'll talk a bit about that later in the script, but often we want to use gradient accumulation if we have few GPUs because we want a large effective batch size. That gives averaging across the batch size, which reduces noise and gives us better training performance. And so for that reason, well, not for that reason, but if we're working layerwise here, it's difficult to accumulate gradients across multiple batches, at least something that's not supported in the software right now. So with that, we're ready to move through a few different examples in code. And I'm going to show you how to do it in a Jupyter notebook, which is suitable if you want to run on one GPU. And then I'll show you very quickly how to run scripts using a rental GPU, like say you rent via RunPod or VastAI. And that will allow you to use multiple GPUs. You can very easily run in distributed data parallel, that's DDP. This is useful if you can fit your model fully on a single GPU. If you cannot fit your model on a single GPU, you need to use fully sharded data parallel. So I would recommend use all the tricks you can to get the memory down. And if that's not good enough, use fully sharded data parallel. And probably the other video on fully sharded data parallel is most useful for you there. I'll note that you can just use the optimizers I talk about today in that other FSDP video. I'm here and I'm working out of the Trellis Research Advanced Fine-Tuning repo. You can get access to this paid repo over at trellis.com. That's trelis.com/advanced-fine-tuning. Advanced-fine-tuning. Now, you can also just run the scripts. They're different, but they're quite similar, and I think you'll be able to follow them from the base Galore repo, which I'll link below, or the Subspace Descent repo here. So what I've done is I've cloned this repo, the Advanced Fine-Tuning repo, into Cursor, and I'm now going to move to the branch for this full fine-tuning. So what I'm going to do is, sorry, I'm actually in VS Code. Here we go, in Cursor, and I'm just going to do git switch, or rather you would do something like git checkout probably, and you would do low VRAM FFT. And let me just check I have the name correct. So go to origin and low VRAM FFT. Okay, I've got it that way. And you'll see in this repo, if we take a look at the README, there are two main types of scripts. There's the Jupyter notebook here, and there's the full fine-tuning notebook that you can use here. I'm going to go through both. It's probably easier to see what you're doing in the notebook, but it's not going to be as good for running on multiple GPUs, whereas this one here is better for running multiple GPUs. So I'm going to head over to RunPod now, start up a GPU and upload the notebook and work through some examples there. If you are interested in a one-click template, you can head to the Trellis Research one-click LLMs repo. This here is a public repo and you can find the one-click template. Then you can choose, I like to choose the cheapest GPU, which is the A40. And you'll see the template is selected here and deploy on demand. Now I've deployed that GPU a little bit earlier, so it's already up and running. And so I'm going to connect to the pod. Later I'll connect it via Jupyter Notebook and show you the notebook scripts, but actually first I'm going to show you the scripts through cursor/VS Code. To do that, I like to copy the SSH command here, go into VS Code, click on the SSH, connect to host. Sorry, not connect to host. Let me try that again. Connect to host. Yes, connect to host, add new SSH code. I'll paste that in, press enter, connect. Then I will git clone the repository, and then I'll git clone it into the workspace folder, and then I'll get the terminal going. So basically here I'm connected and I'm in Advanced Fine. I have switched to the low VRAM FFT branch. So I can just click here. You'll see on low VRAM FFT. And now I'm ready to start running some fine tuning. And I'm going to show you a few different fine tunes, and I'll follow the same order that I have here in the presentation. I'll go through the AdamW, which is the main full fine tune, the highest quality, then the 8-bit, also high quality. Then I'll go through Adafactor. Then I'll go through Galore. Then I'll go through Galore with Subspace Descent. And then last of all, I'm going to show you Galore AdamW 8-bit. Actually, I'm not going to show you with the Subspace Descent, but I will show you Layerwise in a Jupyter notebook. It is possible to do this with Subspace Descent. For that, I recommend you head over to the online Subspace Descent repo. But I just want to show you this in a notebook. You can also run these methods too if you're just running on one GPU in a notebook. So I'm connected up to my GPU. Note that I've got 4 A100s here actually, because I wanted to run some of the tests a bit quicker. I've run them in advance of the video just so I have all of the results ready to show you here. So let's go through the script. We'll take a look inside full fine tuning, scroll right to the top. You'll see I've selected this Phi 3.5 mini model. It's about 7 gigabytes in size just for 16-bit weights, has about 3.8 billion parameters. The reason I picked it is because I can fully fine tune with AdamW on an A40. You cannot do that with Llama. You can fully fine tune Llama if you use the tricks in this video, but I wanted to show all of the levels of tricks or no tricks, which is why I picked Phi 3. The dataset is an instruct dataset, web instruct. I'm going to train for about 1,000 for 500 rows, and I'm going to train with a constant learning rate and then anneal by just for 100 rows at the end. This is a trendy technique. It allows you to train at a constant rate, anneal, and then if you need to pick up again, you can continue at that same constant rate, as opposed to cosine, where it's very hard to pick up your run again. We'll run evaluation on just about 120 rows. I'm going to use a batch size of 4, and I'm going to use gradient accumulation of 16. Now, note that this must be a multiple of the number of GPUs, because I'm going to split the batch across the 4 GPUs. So if I have 4 GPUs, my batch size needs to be a minimum of 4. And then 4 times 16 is an effective batch size of 64. Usually I recommend 32 to 64 for the effective batch size, which is the product of gradient accumulation and batch size. The learning rate is 5e minus 5. Probably it could be 1e minus 4, because Phi is a bit smaller than Llama 8b, so I can afford a higher learning rate. And I'm using no warm-up steps, because my run is quite short, and if I use warm-up steps, it's just going to have a big portion of warm-up, so I'm going to set that to 0. So here we have a function to define the environment that returns the accelerator. This uses Hugging Face Accelerate to determine how to dispatch the model on the devices. We're going to have a full copy of each model on each device because it's small enough to fit. Then we'll load the model in Tokenizer with bfloat16. This works with an A40. It will not work in collab with a T4. You'll have to change that to bfloat. Flash attention will also not work with a T4, so you'd have to comment this out. I've set use cache to false. Using the cache is relevant for inference. It means that it reuses the KV cache to generate new tokens. It's not so relevant for training. It can be for eval, but it's incompatible with gradient checkpointing, so I've turned that off. Now I'm loading my tokenizer and my model. I'm passing in the model keyword arguments up here, printing the model to see the modules in it, printing the trainable parameters, and returning the model in tokenizer. So that's my load model function. Here's my load dataset function. You'll notice I'm streaming the dataset. This means I'm loading just a chunk of the dataset at a time. And I have a function to format the dataset in there. The web instruct dataset has got a question column and an answer column. So I'm setting up an array of messages here that I'll use for training. And I'm going to format them into messages format. I want them in messages format because then I'm going to apply the chat template, which takes in messages here. And it's going to apply the chat template for Phi 3.5 with truncation and padding it to the length of 2048 rather. Next, I have a function to load my eval dataset. I'm not going to stream the eval dataset. I'm just going to load it and have it in memory. So I'm doing that right here. I'll load the training split and then split out a random sample to use for eval. Again, I format the dataset into this array of messages and output a formatted mapped dataset. This is my function for doing annealing. Basically, it uses a normalized learning rate of 1. And then at the very end, it will linearly fall down towards 0, which is what you have here. And this is just returning that optimizer scheduler. So now move on to the main function where we'll actually run all of these functions. We'll set up the accelerator, get the model in tokenizer, ensure there's a pad token, which Llama doesn't have, I think Phi does. Print out the device just to check where the model is. Calculate the total rows, which is the initial plus the annealing, and set up the train and the eval dataset. Now, because we're streaming the data, the model or the trainer doesn't know when the data set's going to end because it only sees the next batch. So we need to tell it the total steps, and the scheduler needs to know the initial steps. You calculate that through the total rows times epochs divided by the virtual batch size, which is the batch size times gradient accumulation. Next, I define a run name using a timestamp, total rows and learning rate, and a function to print the memory usage. Now, I do support using LoRA here because I knew people would like the comparison. So later we'll come back and we'll use LoRA just to compare that in terms of quality and training time. But first, we're going to use the AdamW Optimizer. It's the best quality optimizer that uses the most memory. And we load it like this by passing in the model parameters. That means all the parameters will be optimized and the learning rate will be set using the learning rate that I've defined right up at the top of the script here, the 1e minus or 5e minus 5. So with that, our optimizer is ready. I'm going to comment out everything else to do with the other Galore optimizer because we don't need that. But I'm going to keep in the learning rate scheduler, which sets up, it just calls the function to set up our learning rate schedule with the optimizer, the warm-up step 0, total steps, and initial steps. So now we can set up the training arguments, the output directory, the run name, the logging directory, and I'll show you how we can view that with TensorBoard. We're not going to save the model checkpoints. Normally you would, so you would want to set that to steps instead of no. So you'd want to set it to something like steps for saving checkpoints. You can also set it to epoch if you want to save every epoch, but we've only one epoch, so that wouldn't be relevant. We're going to report to TensorBoard. Here's the max sequence length. The epochs is 1 set above. The batch sizes are set above. It's 4. Although those will be split because we set split batches to true. So if it's 4, there's only going to be 1 going to each GPU. Normally you want to increase that until you run out of memory, but we're trying to measure the lower bound of memory, so I'm just setting that to a low value. This is not critical. It will drop the last piece of data if it's not like a complete batch. It won't make much difference. And here I'm setting the log steps to every 10% and the same to eval steps. Using BrainFloat 16, setting max steps, using gradient accumulation, using gradient checkpointing to save on memory with storing the activations. I can briefly show how that works here in the presentation. Essentially, when we run a forward pass, we calculate activations, which we store and we use then when we do the backward pass to get the gradients. But you can also just throw out the activations on the way forward, save the last one, and then iteratively regenerate the activations. That's gradient checkpointing, which really is activation checkpointing and saves memory significantly. So we're going to take advantage of that and recompute the activations on the way back. That's different than Layerwise. We're still going to save all of the gradients here. We're not going to recompute those, but we are going to recompute activations. Okay, so we're passing in the last parameter here is the gradient checkpointing keyword args of using reentrant. This needs to be off for LoRA. We can actually set it to on if we want to run any of the other configurations. It's just LoRA. If we use DDP, distributed data parallel, it gives issues if we try and use the optimized gradient checkpointing reentrancy. Next, we have the trainer. So we pass the model, the data sets, the arguments, the tokenizer, the formatting instruction, which is the chat template. And we're going to pass in the optimizer and the learning rate scheduler through the optimizers argument here. Then we'll prepare the trainer and we'll start to train. The rest of this is just logging. So I sometimes log out just to show what parameters are in the optimizer, print the memory usage, and then save the model. So with that, this script is ready to run, and we can check the README for the instruction here. Let me just open a preview, see what that looks like. If you want to run, you can run just on a single GPU with something like UV run full fine-tuning, or with Python run full fine-tuning. Sorry, just Python full fine-tuning.py. But we want to run multiple GPUs, so we'll want to go with something like this, accelerate launch. Mixed precision BF16 just tells it that we're going to run with BF16, and we can run like that now. So I've run this before, but I just want to show you what it looks like. You'll see number of processes is automatically set to 4. That's good. One machine, this means one node. We only have one node typically if we're running on something like RunPod or VastAI. Here it's loading the model, it's printing out phi3. Checkpoint shards should be loaded. You can actually see duplication because it's printing out the logs for each of the GPUs. So we see that for all of the GPUs. It's mapping the data. It's showing us the memory after the models are loaded, which is about just over 7 gigabytes. Makes sense because it's 3.8 million parameters. And now starting the fine-tuning. And at the very start of training, the GPU has not increased memory. But once we get towards the end of training, and I'll let it run through for a bit, we're going to see the memory should go up and we'll get some result for that training. Now, in the meantime, I'm going to take you right to the results, which we can check out on TensorBoard. And I'm going to highlight the ones that we have. So the result in question here, and I'm being blocked, unfortunately, by my recording screen. So the first result we want to look at is AdamW, and we're going to focus on training. You can see here from earlier, we've that constant learning rate, and then the learning rate decreases here at the end. That's the annealing right at the end. And here's our training loss, which is decreasing as you might expect. And notice how it kind of decreases rapidly at the end. That's a sign. Notice how at the end we have this rapid decrease. That's a sign that the annealing is working. And indeed, annealing does work. If you slow your learning rate at the end, you will get better results. And so with that, we now want to compare the next type of training, which is going to be, with that, we'll now compare using the 8-bit optimizer. So we'll now compare with the 8-bit optimizer. So I'll head back to my script. With that, we'll compare now the 8-bit optimizer. So I'll head back to my script. I'll comment out this AdamW optimizer. To swap in the 8-bit one, we'll just uncomment down here, AdamW 8-bit. And you'll see this optimizer is imported from the bits and bytes library, whereas the AdamW one's imported from PyTorch. There's nothing else that's different, and there are no changes that need to be made. So with that, I'd be able to proceed and run the same script, just save those changes and run the script here, which is accelerate launch, mixed precision, full fine-tuning.py. Now we can take a look at the results. We can take a look at the results from that. So let's add on here the AdamW with 8-bit. So now you can see in light blue, I've added AdamW 8-bit, and it's remarkably similar. The training loss is pretty much overlapping. The grad norm is maybe a little bit higher in the light blue, but really there's not a whole lot of penalty that we're seeing here for using 8-bit optimizer states. And I know this is small. In fact, I could increase my screen size. AdamW took me 43.7 gigabytes. AdamW 8-bit brings it down to 29.8. So we have a very significant reduction in VRAM just by using the 8-bit optimizer right there. Let me scroll down to the training loss. So that's the 8-bit. I'll now show you how to use Adafactor, which is a little bit different. So we'll comment out the AdamW Optimizer. And there are two ways to use the Adafactor Optimizer. The first is you can comment in Adafactor here, and you can pass in the model parameters and the learning rate. Now there are two parameters to look at here in Adafactor. Typically, if you set the learning rate, you want to set the scale parameter false and the relative step to false. The scale parameter here effectively sets the learning rate differently for every parameter. For big parameters, it sets it to be large, and for small ones, it sets to be small. It's kind of an automatic learning rate. And the relative step here is kind of like the scheduler. It will set a 1 over square root of test type curve instead of cosine or constant. But we're defining the learning rate, so we need to set these to false. And with that, we can just run with Adafactor here. So I've run that earlier on, and we can add that to our list of results. I've run Adafactor earlier on, and we can add that to our results here in orange. And what you'll see is that Adafactor is not performing quite as well. It's a little bit above, not hugely above, but a little bit above the loss of AdamW and AdamW 8-bit. Now, something I did try then is I said, well, what if we use the default Adafactor parameters? So instead of setting a manual learning rate ourselves, what if we use the Adafactor defaults? And this means we don't set a learning rate at all, which I know is unusual. And we just allow it to set the learning rate based on the size of the parameters and based on this 1 over square root of t relationship. So the easiest way to do this is actually to comment out the optimizer entirely. comment out our manual learning rate scheduler because we don't need that. And then select Adafactor here. So we just pass in the Adafactor optimizer and we comment out then passing in a specific optimizer that's been set up with our learning rate schedule. So here we're allowing the learning rate to be set automatically by Adafactor. And this turns out to be a good approach in this case. If we turn on the auto learning rate with Adafactor, you have here in yellow a line that is pretty much overlapping with the learning rates or with the training loss of AdamW and AdamW 8-bit. So actually Adafactor does very well in this case. I believe it's known that Adafactor is not as stable, perhaps particularly in early pre-training, and therefore it's not favored usually over AdamW, but it does use a lot less memory. Adafactor uses about 23.3 gigabytes, so even less than AdamW with the 8-bit optimizer. And you can see the results are quite good here, at least on the auto learning rate. So next, we're going to start to look at some of the Galore techniques. So I'll have to comment back in the optimizers here, comment out Adafactor, so we're not going to use that. And we're going to go back to using the same learning rate schedule that I had previously. Now, to make use of Galore, I'm going to have to comment in those lines. So I'm going to comment in here for Galore, all of this code here, which I'll step through briefly. So first, I'm importing from the Galore Torch library. I'm setting up which parameters to apply Galore to, which will be the linear layers, and then the parameters not to apply it to, which will just have the full 16 or 32-bit optimization applied to it. So here, we're going to go through all of the modules and pick out the ones that are linear layers and set those as Galore parameters and set the rest as non-Galore. Then we set up the optimizer by passing in the non-Galore parameters and the Galore parameters. And we need to pick the size, the number of dimensions that we're going to reduce the gradients down to. So instead of say 2000, it's going to go down to 512. And we need to set how often we calculate this projection, which is the singular value decomposition. Now there's also this scale parameter here, which is a multiplier on the Galore parameters. It's kind of like the multiplier alpha we use for LoRA, where we can have a higher learning rate on LoRA parameters than others. Here we can have a higher effective learning rate on the Galore parameters compared to the others. And in my quick tests, it seems like using a higher value does do better here. So even though the range of 0.25 to 4 is recommended, I would probably put it at the higher end of the range with the logic that when you're optimizing in a reduced space, you're probably going to move with smaller steps, and we may want to accelerate that just because we've a reduced space compared to the full range of dimensions. Now, if you're using standard LoRA with standard value decomposition, you actually need to, set the projection type to be standard. This means that it's going to use singular value decomposition. Whereas if you want to use Subspace descent, you need to set the projection type to continuous. And you also need to set an array for the value of names here. I've just set it to none, but this will throw an error if you don't set it. For now, we're using the standard method, which will be slow. It will be slow to set up initially because it has to do SVD, and it will be slow every 200 steps. But everything here is now set up. We're passing in the learning rate schedule, and we're passing the optimizer then into the SFT trainer here, along with the learning rate schedule. So with that, you're ready to run Galore. We'll run through now how that looks. So again, with a green baseline of the loss for AdamW in full precision, we can take a look at AdamW here with a rank of 512. And you can see that Galore is not quite as accurate as AdamW, presumably because we're only doing optimization, we're storing optimization parameters in this LoRA subspace. Now notice that if you decide to lower alpha down to something like 0.25, you get significantly slower convergence. So here in dark green at the top, we have alpha of 0.25, whereas in gray or black rather, we have 4. So this is why I think it is important to set the alpha parameter to something like 4, maybe rather than 0.25. Now I looked at a few other ablations as well, like using a lower rank here in purple, which is even worse. That's a rank of 32. And you can also check an intermediate value of alpha. Although I should mention both of these graphs here, the purple and the green, they're not just using different values of alpha, they're also using 8-bit. So broadly speaking, if you use Galore, you're going to get reasonably good results. Let me show you again the original Galore. It's pretty close in terms of the training loss by the end here, but your memory is 26, which is significantly lower than using AdamW with 43. Now note how interestingly the Adafactor approach is allowing you to get down to 23 without even changing the gradients. I'll show you that one here again with the auto learning rate, and the quality of that is very good. And also the 8-bit Adam, which is 29 or 30 gigabytes instead of say 26 for Galore, is also very good. So yeah, we're seeing some degradation here if we do decide to use the Galore approach. The next approach is we take Galore and we use the subspace descent. This is going to mean it's going to be faster to run because we only have to run the singular value decomposition first at the start. And it should also be better in terms of convergence over time because we're continuously updating the choice of dimensions in which we want to optimize. So to do that, the change that we have to make is actually just in how we do the installations. I should have mentioned that before you run Galore, you have to install the Galore library. You can do that with pip install Galore torch or uv pip install Galore torch system. But if you want to use Galore with subspace descent, you should uninstall that Galore package, clone the online subspace descent repo, cd into it, update your requirements, and then copy the full fine-tuning script into that repo so you can then run it. And so if you've run all of these installations here, Galore torch will be available with the online subspace descent capabilities. And I'll show you now what that looks like. So we can take a look now at how those results look. So we have the AdamW loss here, and we have AdamW using Galore, so Galore AdamW. And now we're going to compare subspace descent, which is in purple. And actually you can see subspace descent is maybe a little better earlier on, but for some reason over the last few steps, subspace descent is actually diverging to be a little bit worse. Again, this is a really short training run, so I wouldn't put too much credit into it, but it seems like we're not seeing a whole lot of difference. Granted, we're only running over 22 steps, which is much less than the update frequency that we would use for SVD in the standard Galore approach. Broadly speaking, though, I would say the quality of these approaches is roughly comparable. Now, before I wrap up with the scripts here and move quickly to the notebook, there are many optimizers you can use with Galore. I've used Galore AdamW. You can also use Galore AdamW 8-bit for a little bit lower quality but less memory. And you can also even use Galore Adafactor, which should get the memory savings both of Galore and of Adafactor. So you can just choose these by swapping in your choice right here, and there's very little else that needs to be changed. Just one note, I said it when I went through with the Galore optimization. If you're using standard, which is going to update every 200 steps with a slow SVD calculation, you will leave standard. If you want to use the Galore with subspace descent, you'll have to comment in continuous and this parameter here for names. And so last of all, I'm going to show you how to run the notebook. The notebook here, the low VRAM full fine tuning. Quite simply, you can head over to a pod if you're running it, click on connect, connect to the Jupyter Lab, and upload the notebook here. The notebook follows pretty much the same structure as the scripts, except it's only set up for running on one GPU. In fact, I explicitly will tell the notebook that there is only one device that's visible if I'm running with a set of 4 GPUs, because it will fail if I try to run it on more. So here we have the same setup. We're using Phi3 Instruct Mini, and I want to show you how to run that Layerwise example. So what I'm going to do is just restart the kernel so I know I'm starting fresh. I'm not going to use subspace descent, but I am going to use Galore torch, so the basic version using SVD. And I'll show you here with optimizers. I'm going to comment out all of my optimizers here. And quite simply, I'm going to pass in Galore AdamW Layerwise and pass in the target modules, which will be all linear. You can see I've commented out passing in optimiser and learning rate schedule and commented out the same there. So I'm just using a default learning rate schedule that is offered by Galore AdamW Layerwise, which should, by the way, I think be a cosine learning schedule. So with that, I'm going to run. So Shift and Enter. And I'm running that. Just make sure that you run the cell that says CUDA visible devices equals 0, because otherwise that will generate an issue if you try and start the script with multiple GPUs. So we'll see here the model, the Phi model. It's been loaded. The memory is about 7 gigabytes, which is what we expect for 3.8 billion parameters in 16 bits. And it's now going to start the fine tuning. It's using Galore, so it's doing this. It's doing the singular value decomposition, which takes a significant amount of time. And that's why we have this kind of hold up at the start of the training. But once it's through that, it should move pretty quickly through the relatively short number of training steps that we have. Now, while we wait for those results and to check the VRAM, I'm going to show you here the result using LoRA. I did run through the whole script using not just LoRA, but also training the embedding parameters, because it's known that LoRA by itself on the linear layers is always often insufficient. So you'll see here what I did was I commented in LoRA, trained all the linear layers with LoRA adapters, and then trained in full the language model head and the embed tokens. Notice that if you uncomment here, you'll also want to uncomment passing LoRA into the trainer, which is just down here. You uncomment PEFT config and make sure that you've installed PEFT. This is all described in the README. But the result you get when you turn on LoRA, I'll just turn it on here, is not very good in this case. We're seeing that the model, the loss is falling a lot more slowly. Now, there's an argument here that maybe you should increase LoRA alpha, and you might be able to get the model to start to train at the same rate as the full fine-tuning. I haven't done that full ablation, so I can't rule it out. But I am using rescaled LoRA. You can read more about that in LoRA versus full fine-tuning. So I think that my alpha is already fairly high. And in this case, it does seem LoRA is not converging quite as well as the full fine-tuning. I wouldn't say LoRA is necessarily always bad, though. Sometimes it's quite small, the difference it makes with full fine-tuning. But probably in general, full fine-tuning does give the highest accuracy. The gradient projections have been calculated and we are now training. So the SVD step is over. And this is progressing quite quickly. It's only about a minute in order to do roughly 82 steps of fine-tuning. So we'll just see what the memory requirements are with this layer-wise approach. It should be the lowest value of all of the runs that we've done so far. Just as a brief recap, with the full Adam, we had 43. With LoRA, we had 18.5. With Galore AdamW using Subspace descent, we had 26 gigabytes. And the same amount whether or not we use Subspace descent. And the other approach that we're interested in is the Adafactor one, which is listed up here. And Adafactor used 23, so less than using Galore. And the quality was quite good as well. So let's head back and take a look at the memory requirements with that training done. And you can see here that with the memory over, we've only used about 14.3 gigabytes. So yeah, training Phi 3.5, using the Layerwise approach, it's really cutting the memory down. As I said originally, we had with AdamW 44 gigabytes. That came down using Galore down as far as about 26 or even 23 if we use just Adafactor. And now we're down to 13 if we do the Layerwise. So that just shows you when you pile all of the tricks on top of one another, that's the 8-bit optimizer. Then on top of that using Galore and on top of that using Layerwise, you're able to get the memory requirements down by a lot. Now, I should mention that you can also use the notebook in order to push your trained models to hub using this script here, or to inference the fine-tuned models. For example, I'll just do a quick inference on one of the models I created earlier. Let's say the Adafactor 2.3, 23.3 gigabyte with the automatic learning rate. So I've set that up as one of the options. And if I do Shift and Enter, I can select to run that model from the local path. It's going to load the checkpoint shards. By the way, you can see the models are not stored there, but they're in my advanced fine-tuning Trellis local folder because I had saved them from cursor. So the model we're running is the Adafactor model right here. And you'll see the model is almost loaded now. It's printing out just the tokenizer's details. And next it should move to inference. What's the capital of France? Paris. Explain the concept of gravity. Describing gravity. Derivative of a function. Okay, it's truncated because I've limited it to 50 tokens of output. But yeah, you can see all of the inference is working well here. Let's see if I save the model from the quick training I just did. I'm not sure, I may have commented that out. Yeah, I did train it, so I don't actually have that model available, but if I did, it would have been saved into the Trellis local folder, and you'd just be able to select that model by typing it in here to the local path, or you could decide to inference a model that's on Hugging Face Hub just by putting the slug in here and then Shift Enter and pressing number 2 for that Hugging Face Hub model. And with all of that, we can move to some final recommendations. So if you're running on a single GPU, my recommendation is if you need to minimize memory, use Galore AdamW with Subspace descent and use the Layerwise approach. That will get you the lowest amount of memory. It's going to be well below 20 gigabytes if you're fully fine-tuning Phi 3, and you'll definitely be able to fit even Llama 8B on a 48 gigabyte GPU. In fact, Llama 8B should only take just over 20 gigabytes. I'll caution though that Layerwise does not work for multi-GPU. So if you have a model that won't fit on one GPU and need to use fully sharded data parallel, you cannot use the Layerwise approach. It also won't work with gradient accumulation, in which case my recommendation is to keep the batch size as big as possible without running out of memory. Increase it until you run out of memory, as far as ideally 16, or even probably you won't manage to, but 32 would be nice. In terms of the best GPU for a multi-GPU setup, I recommend, in terms of quality, probably AdamW is the highest, but I'm not sure you're trading off much in quality by using AdamW 8-bit. To some degree, you get a very large reduction in memory by using the 8-bit optimizer without probably compromising too much on quality. Furthermore, if you want to reduce memory, you can use Galore AdamW 8-bit with the Subspace descent. And I'll just note, if you don't use the Subspace descent for bigger models, you are going to have a lot of slowdown because of the singular value decomposition calculation that needs to be done. Another interesting option is to consider Adafactor. You don't have to even change the gradients. You can just use the Adafactor optimizer with the dynamic learning rate, and you'll get right down to 23 gigabytes. So you can greatly reduce the memory requirements and probably fit on quite a lot fewer GPUs just by swapping to the Adafactor optimizer. Although I'll note, even though it looks good in my really quick ablation, I'm not sure that it will be quite as robust if you're doing a training from scratch of some of these models. Now, just some notes on multi-GPU for those who want to go on and watch the fully sharded data parallel video. The rule is, if your model fits on one GPU and you've used all the tricks to get it on one GPU, that's great. You can now use distributed data parallel, which is the PY script that I showed in this video. That's excellent because it's very straightforward and you'll be able to get training moving without shuttling much data between the GPUs. However, if the model won't fit on one GPU, you need to use fully sharded data parallel. You can use the video on that and just drop in a different optimizer. For example, drop in the Adafactor optimizer to reduce the optimizer memory requirements, or you could even use the Galore optimizers if you follow the steps in this video here. And that's it for this overview of how to reduce the number of GPUs you can do your full fine-tuning on. I'll leave the resources below, the original Galore repo, also the Galore with Subspace descent, and the links to the Trellis Advanced Fine-Tuning repo. Let me know any questions below. Cheers.